Oh, you mean like one by really? I'm so mad about that. No, I'm so mad about that. This was so good. You get that? No. Oh, like my bad. It was a bad. Okay, wait. Okay, well, it was some like question online. And it was an 8, and it says paper phobia. And she was an 8. And I was like, it's like lots of quantity. I think like for like, I don't know when that's I like for DNA or something. And she still doesn't. She's like, oh, 17, I want to go to like. Be able to play, but I don't think it's like about them. Like I literally told her. It makes sense. But you at least need to learn it more. Yeah, like I would. So like science, be smart on science. And then if it's. And he doesn't know, and I like. Ionic bonding is between positive and negative. And I think covalent bonds, I mean, it's like bonding with things like that's not like what's. Doesn't even matter. And you can try whatever I no, yeah, exactly. And then she was like, so what if these one that he is done? I was like, no, it's not. She was fine. I said, like, it's not bad for her. Because also she's on. Lord.
All right, guys, page 18. Okay, so we'll talk about derivative of inverse set of points, and then we'll go back and extend some of the implicit differentiation problems from yesterday. So I think that's all I want to cover today. Yeah, and we'll save the derivative inverse trig function for next Tuesday. Okay, so. All right, so function's inverse is found by swapping the input and output values. So when you swap your x and y values and you create your new equation, you're going to get an inverse function. Your domain and ranges are also swapped between a function and its inverse. So for instance, if we want to find the inverse of y equals 6x plus 2, we would swap the x and y. And then solve for our new y variable. So subtract 2, and then divide by 6. So now we call that new y variable if f inverse of x is equal to x minus 2 over 6. So basically what we've done is all the x and y order pairs that are on the function gets flip-flopped on the inverse function. But for us, the most common inverse relationship that we're going to see is between e to the x and natural log of x. I can sit behind. Yeah, x. But for now, let's just talk a little bit more about a function and its inverse. So here's an example of an inverse function. You have f of x, you have inverse of f of x. A function and its inverse, you can always fold the graphs over the line y equals x, and they're always going to perfectly overlap. So let's say there's an order pair on the function called at 1, 2. It's not perfect, but I just say this is a 1, 2. Okay. On the inverse function, there must be an order pair that's what? 2, 1. Yeah. So if it's a true inverse function, you can always flip-flop the order pairs, and they're always going to is always going to live on the other graph. Okay. So between a function and its inverse, I like to create this chart to kind of help. And this is for later on as well. That let's say there's an order pair f of 1 is equal to 2. There must be an order pair on the inverse function that is 2, 1. Okay, so we know that at the function level, they're always going to be that order pair relationship. Now, from a derivative standpoint, from a slope standpoint, there's also going to be a numeric relationship between these two at these 2 points. Okay, so let's just say there is a slope of 7, or let me change that. Let me say the slope of 3. So let's say f prime of 1 is equal to 3. Okay. It's not, yeah. And maybe this is not a perfect instance here, but if this is a slope of 3, if you had to guess, if you knew that there was a numerical connection to this number, what do you think this slope could be here? 1/3, and that's it. That's the relationship here between if there's 2 points that are what I call these corresponding points between a function and its inverse, their steepness at their point will always be reciprocals of each other. Notice that they're both positive. It's just one is, so it's not quite opposite reciprocal like what we think of with perpendicular lines. It's always just going to be reciprocal. And that's really the whole relationship that we're going to talk about today. So if f prime of 1 is equal to 2, then the derivative of f inverse at 2 is equal to, sorry, my bad. I put the order pair there. If f prime of 1 is equal to 3, then the derivative of f inverse of 2 is going to be 1/3. Okay. But the way that the problems are going to be presented, we're going to kind of be we're kind of searching for information, and we're going to be kind of working our way around this table until we have enough information to get to our final result. So I'll show you the flow of how what information is presented, and how we're going to kind of gather our way around. Right. So this is kind of in a notation wise of what we're going to be finding. The problem is always going to ask us to find the derivative of inverse at a point. And we know that that point, that x value they provide us, is really the y value of the original function. Right. So there's going to be kind of like a mismatch information to start with. The problem is going to provide us the inverse. It's going to ask us about the derivative of inverse, the slope of inverse, but they're going to provide us the original function. So the problem is going to a lot of times force us to use the original function and make a conclusion about the inverse. So if there's an order pair b comma a on the function, there must be an order pair a comma b on the inverse. And then we're going to be working on the function. We're going to find the derivative. A lot of times it's just power rule or chain rule. And whatever slope we find, let's call that n. Once we find that slope, we don't have to do any more work. We know that the inverse at its corresponding point must be the reciprocal. Okay, so a lot of times we're just kind of working our way around this chart and then gathering information. And by the time we come back around, we're going to have enough data to make our conclusion. There's also a derivative formula that the book provides, but I don't like this one as much. because it just feels like there's too much going on, but I'll just write it out. I like this chart here because it kind of allows us to kind of gather information one piece at a time rather than trying to do everything at once. Okay, so it's 1 over f prime of f inverse of x. All right, example B. Our function is x cubed plus 4x plus 2. We're trying to find the derivative of f inverse at -3. So one thing we have to know is a lot of times we're not going to be working with the inverse function. We just know that we're going to be getting most of everything that we need from the function level and then just making our final conclusion on the inverse. But I like to start off with the chart here and just kind of identify what I have to begin with. So I know this is my end result. My end result is going to be this bottom right corner here. I'm trying to find the derivative of f inverse at -3. Okay. By the time I work my way around this chart, I'm going to have enough data to fill in what that slope is. But right now, -3 is the what value of the inverse function? X, yes. Okay, so I'm going to have order pair information up at the first row, and then the slope information in the second row. So I'm going to say f inverse of -3 is equal to. So this is slope, and this is order pair. Now, if -3 is the x value of my inverse function, then -3 must be the what of my function, the y value. So I'm just going to fill in this information here. So without even looking at my function, if this is all I have to begin with, I can fill my chart up to this point. I know that ultimately I'm trying to find the slope of my f inverse at -3. I know -3 is the x value of my inverse, and I also know -3 is the y value of my function. Everybody okay so far? All right. Now, this is what we're going to be working with. We're going to be working with a function, and we're going to try to figure out, okay, if I can fill in this slot, then everything else is going to fall into place. So I have the y value of my function. This is my f of x that's given to me. So I'm just going to set these equal to each other. Okay? I have my y value, and I'm trying to work backwards to figure out the x value of my function. Okay? We're not going to, again, these problems, we're not going to work on the inverse side of things. We're going to do everything on the function side, and then we'll make our final conclusion. So we'll say -3 is equal to x cubed plus 4x plus 2. Let me bring everything over to one side. So 0 is equal to x cubed plus 4x plus 5. Sometimes the equation you can solve using factoring or using algebraic steps, but sometimes it's a problem like this where it's not easily solvable. If that's the case, and you don't have a calculator, you're going to go through a series of guess and checks. You're going to try a few numbers, and then eventually you're going to find it. It's going to be an easy number to find. It'll be an integer value that'll be close to 0. Okay, so test 0. If 0 doesn't work, then test 1. If 1 doesn't work, then test -1. After a few tries, it'll be a nice integer value between -3 and 3. Okay. They have to make it easy, especially if if we don't have a calculator and if we don't have a nice algebraic way to solve. So let's just try a couple of numbers, and eventually we're going to get it. Okay. So would 0 work? No, right? If I plug 0 in, I'm not going to get the two sides to work out. Okay. What about 1? Would 1 work? No. Okay. What about -1? Yes. Okay. So if I plug -1 in, -1 minus 4 is -5. -5 plus 5 is 0. Good. That works. So now I can fill in my order pair that lives on the graph with a y value of -3. Must be the order pair of -1, -3. Which means that on the inverse side, there must be an order pair of what? -1. Okay. We don't really need this side. I just like to have this side filled in just so that I can kind of have that anchoring. Okay, I know that I see the two order pair relationship, and it's nice to see that with a function and its inverse. So now I'm going to move down to this is the derivative information, right? So if I can find f prime of -1, then I'm almost home free. Then whatever slope I get, I can do a quick adjustment to get the slope that I really want to get. So before I can find f prime of -1, I first need to find what? Yeah, f prime of x. So we'll do f prime of x. This should be an easy power rule here. What's the derivative? Okay, 3x squared. Okay, 3x squared plus 4. Okay. All right, we have the slope formula. We have the x value that we want to target. So let's do f prime of -1. And what do we get? 7. So if the slope on the f graph at -1 is giving me a slope of 7, then the slope of the inverse at its corresponding point, -3, must be what? 1/7. So that's our answer. All these problems, we're going to kind of follow that pattern. Okay? And there's going to, it's going to be the same setup every time. And sometimes we can solve this by hand. If you can't solve it by hand, then just start testing your nice integer values, and eventually you're going to find it. Any questions so far? All right. Let's look at next example here. Here's our function. We want to find the derivative of f inverse at 1. So again, I like to start with my chart here. Now I'm trying to find the derivative of f inverse at 1. And I'm just going to work my way counterclockwise around this chart. As I gather enough information, eventually I'm going to get to my answer. Okay, order pair, it's going to, data will live up top, so I can fill this in. And then on the function side, I can say what? F, yep, equals 1. Okay, so before we do anything, this is how we can always start our table. All right, what's our next step?
Set that equal to 1.
Good, set that equal to 1. Okay, so 1 is equal to the square root of x cubed minus 7. I think this one we can solve by hand. Right. What can we do to both sides of the equation? Square, yeah. Add 7 to both sides. Take the cube root. X equals 2. Okay, so there's the order pair 2, 1, which must mean on the inverse, there must be order pair 1, 2. So if I can find f prime of 2, then that slope will lead me to my answer. But before I can find f prime of 2, let's find f prime of x. But before I find f prime of x, let me get my function ready for my derivative. How can I rewrite this to get myself ready for my derivative? Good. And what do we have to go through? What process do we have to go through to find the derivative? Chain rule, yeah. So set up your outside derivative, multiply it by your inside derivative. Then you can plug in 2 into your derivative function. Right, bring down the 1/2. Keep everything inside the parentheses. Raise to the negative 1/2 times, what's my inside derivative? X squared. We'll do some cleanup. Replace all your x values with 2, and that should get us to our slope. So use this space here, I'm running out of room. So f prime of x, if I do some cleanup here, you don't have to do cleanup. I just wanted to find it a little bit easier if I can clean up, so it'll make it easier for me to plug in. So there's my cleaned up version of my derivative. I'm putting the 3x squared up top. I'm putting the 2 below. I'm putting the parentheses to the 1/2 in the denominator as well. Right, plug 2 in for x. If I plug 2 in for x, this is actually going to clean up nicely because 2 cubed is what? 8. 8 minus 7 is
1.
and the square root of 1 is still 1. Okay, so that's going to come out cleanly for us. So I have 3 times 4, which is 12. 12 divided by 2 is 6. So if the slope on my f side is 6, the slope on my inverse side must be 1 over 6. Okay, so never change the sign, keep the same sign, and just flip that fraction or flip that value. Okay. Questions? Sometimes the problems are even easier than that in the sense that all the values are given to you and you just have to be able to fill out the chart and then gather the data. So let me show you what that looks like so this is page 19. Let G equals F inverse of X. So whenever you see this, you know that you're dealing with a function and its inverse. What is the value of G prime of 1? So look, if you look here, they don't give us anything about G of X, but it's okay because we have F of X to make that connection between F and G. So let me create my table here. I'm looking for G prime of 1. So that's going to go in my bottom corner here. I know 1 is the X value of my G function, which must mean that 1 is the what of my F function. Yeah. And the reason that we can establish that relationship is because they're giving that to us. They're telling us that G and F are inverses of each other. So we know that there's going to be that flip-flop order pair. So G F of something must be equal to 1. Right, so this is our key to our chart here. What order pair will allow us to fill this piece in? 2, 1, right? We know that on the F graph, whenever for the Y value of 1, we're working backwards and figuring out, okay, the only thing that fits is 2, 1. So if there's an order pair 2, 1 that lives on the function, there must be an order pair 1, 2. And if I can find F prime of 2, then that's going to lead me to the answer I'm looking for. What's F prime of 2? Yeah, F prime of 2 is -2. So therefore, G prime of 1 is -1/2. And then number 2 says write the equation for the tangent line. So of F inverse, which is G functions. So we have everything that we need on the inverse side. So our order pair is 1, 2. Our slope is -1/2. And then we should do point slope form. Okay. I'm going to do a second. You need to pass. All right. Any questions? All right. So try number 3, and then see if this whole chart process makes sense. If you get stuck, it's okay. I'll go through each of the parts with you, but try number 3, and see how far you can get. Oops. Not F. This one should be G. And also, if they give you a bunch of order pairs, just be aware that sometimes there are some distractors. There are some order pairs that we're not going to use. So just be aware that there are some order pairs that are trying to throw you off. Okay, I got -1/2. Any questions? No. All right, try number 4. Okay, I got 1/36. Any questions? All right, let's see if we can finish the rest of the page, and then we'll go back and do some more implicit differentiation. For 13 and 14, at the top here, they're establishing that G and F are inverses of each other. So we know we can go through those steps because of this established relationship. The biggest mistake I see that students make with these types of problems is um, taking the x value that's provided and wanting to put that x value in the x value on the other side, and that's where everything kind of falls apart. So just keep reminding yourself that even though this is the x value of the inverse, it's really the y value of the original function. So if you can, I think that's the hardest part. You can just see that relationship there, then everything falls into place a little bit better. So yeah, keep reminding yourself that even though they give you the x value of the inverse, it's always considered the y value of the original function that you're working on. Okay, any questions? All right, if you can turn to page 14, I want to do a quick review over implicits. And then I want to show that we can also find a second derivative involving implicit, which is a little messier, but I think it's good for us to practice that. So let's turn to page 14. And let's do 15. So page 14, number 15. No questions here. Everybody good? So 15, it says find dy dx, find the derivative. And even if the instruction doesn't indicate that this is implicit differentiation, we should be able to tell that these are all implicit because either the y is out of place or the y is mixed in with the function, or there's multiple y's or y raised to a different power other than one. And here you have y mixed into the equation, multiple y's as well. So anytime your y's feel out of place or something strange about the y's, that's an indication, okay, I need to do implicit here. So 15, power rule, but this, we got to go through what? Product rule, yeah. And just be careful that there's a minus in front. So when you build your product rule, protect it with a set of parentheses because you do want that negative to distribute. It will turn both of your product rule terms to negative because there's negative in front. Okay, so go ahead and try this as I work through it alongside you guys. Notice that there are two y variables to begin with in the equation, which means that you should be expecting two dy dx's to pop up. And then once you have that, then your calculus is done. The rest of it is just organizing it, rearranging the terms so they can factor dy dx out and solve for dy dx. I do want to point something out. Sometimes students want to collect the dy dx on the right side, which is perfectly fine. Either of these are fine. They're just the signs look a little bit different. But what I do want to point out is that let's say you got to your version, and then your answer choice is, let's say it's multiple choice, and you're on the AP exam, it's not showing this option. So you could be at the correct answer, but it's not showing up because the signs are different. So if you want to get to a different version of your answer, just multiply the top and bottom by -1, and that will give you a different variation of your answer, and that might fit better with the answer choice available. So just be aware of that. Sometimes, depending on which side you select your dy dx, the signs that you get may be different than the signs on the answer choice. But you can always get from one version to the other by multiplying top and bottom by -1. Okay. What I want to show you is the ability to find a second derivative beyond this. So sometimes with implicit, you may be asked to find a second derivative after the first step. So we just have to go through the derivative process again. So let me show you what that looks like. You can turn to page 47. Sorry, page 15, number 47. Okay. So page 15, number 47 says find y prime and y double prime. Let's just focus on finding y prime first, or dy dx, and then we'll talk about that second derivative. Okay, so again, we know there's implicit involved because there's something off about the y. There's something additional with the y here. So let's find dy dx first. Right, this is my halfway point. Any questions so far? Right. Now, if I want to find the second derivative, they say y double prime, which is fine. I want to show you a different notation for y double prime. It looks strange here. It's d2y over dx2. This doesn't mean to square my derivative. This is just a notation for the second derivative. So all right, so we want to find the second derivative. So dy dx, basically y prime turns into y double prime. So we say d2y over dx2 is equal to. Now, if I want to find the derivative of this, what's involved here? Quotient rule, and again, there's a y out of place, so there's another set of what? Implicit. Another set of implicit is going to show up along the way. Okay, but we said quotient rule, right? So let me set up quotient rule, and I'll walk through it step by step with you. Okay, f prime. What's f prime going to be? -1, okay. G function, just a y. Back to f, -x. G prime, dy dx, okay. All over y squared. Okay. This isn't so bad, but we still want to do some cleanup. Okay, so as we do some cleanup, we're gonna do some substitutions. We may have to do some common denominators, and I'll show you how the problem can clean up to something more simplistic. But at least we're done with the calculus. Okay. What do you think I can replace dy dx with? Yeah, -x over y. So we're going to try to represent our second derivative purely in terms of x and y, and we can do that because we have a substitution available for dy dx, which is -x over y. It's going to create a complex fraction, but we'll just work through it step by step. I'm going to do some cleanup along the way here. Okay, good so far? All right, let me do this. -y minus x squared over y all over y squared. Okay, I want to clean all this together. This is kind of like what we did with complex fractions before, where we're going to kind of clean this side up first, and then we can have an easier time kind of merging things together. So I'm going to work on doing a common denominator to merge these together. So -y over 1 minus x squared over y. My common denominator is y. So this ends up, this denominator needs another y to balance it out. So -y squared, and then this one stays the same. So now I'm going to take this and replace my old numerator expression. Now, taking this, dividing by y squared is taking same thing as taking this and multiplying by the what? Reciprocal. Okay, so at least that kind of gets us at the same level, makes it easier for me to see what can combine. So I can multiply the denominators together. Negative. So our second derivative is this -y squared minus x squared all over y cubed. But there's actually one more substitution that we can make to make our answer look even simpler. Anybody see something with the numerator that we can do beyond this in terms of replacing it with something that looks cleaner? Has to do with the original equation. Yeah, so if I factor a -1 out, I can make this y squared plus x squared. And then the x squared plus y squared can be replaced with 4. And then I'm left with -4. So d2y over dx2 is equal to -4 over y cubed. Now, free response, you're not going to have to worry about getting all the way to this point. I'm just saying, but you know, if there's multiple choice, right, they could get all the way down here, and then you just have to be able to pick that answer choice. Okay, your homework. Let me adjust it here. So your homework, this is due on Tuesday. I'm just gonna make it page 14, 15 all.
Still gonna do this till like. Good job. I grabbed one day, so I came back and he was like, "Do you make your chart?" And he was, and I was like, "What's this?"
You guys are alright.
No, I've never.
Closer for you to